Hi, everybody. This is chapter 8. The chapter is about magnetism. And this is the summary. And in it, we're going to study the following topics: interactions between electricity and magnetism, principles of electromagnetism, applications of sound and sound reproductions, digital sound, electromagnetic waves. We'll study the whole spectrum from radio waves to gamma rays, black body radiation, and detection of warm objects with astronomy. Let's go ahead and start. All right, 8.1 magnetism. Magnetism was first observed in a naturally occurring ore called lodestone. It is thought that the Chinese were probably the first to discover that a piece of lodestone is going to orient itself north and south if suspended by a thread or floating on some water. And because of this, the compass evolved, and this totally changed navigation, maritime navigation, because it meant that you could navigate even in cloudy weather when you couldn't see the stars. Because prior to this, one would have to navigate by the stars, by familiar stars. For example, the North Star was always thought to be due north. But after the discovery of these magnetic ores, the compass was created, and it changed maritime navigation forever. All simple magnets display one common property. That is, one pole, one side is going to be north, and one is going to be attracted to the south. And even if you break it, you still get one side north and one side south. So you can keep on breaking it ad infinitum, and you'll still have a north pole and a south pole. There's been so far no discovery of a monopole material. Metals that are strongly attracted by magnets are said to be ferromagnetic. Okay? And you can induce magnetism in an iron, for example. If you bring it near a magnet, you can induce magnetism in it. Okay, it's useful to use the concept of a magnetic field. It's produced by a magnet, and it acts as the agent of the magnetic force. So you can map these out. And if you would, please, I urge you to look at your book, Section 8.1 on magnetism, page 293. If you look at figure 8.5, you'll see a very nice mapping out of a magnetic field lines. The Earth's magnetic field has about the same shape as the field lines around the bar magnet, obviously much larger. But it's not quite at the due north. It's not at the North Pole. It's about 11 degrees off. So that's why you have to use a declination when navigating with a compass. So you have to know where you are on the Earth. The Earth, that north needle will point towards that 11 degrees off of due north, and you have to compensate for this. And it's called magnetic declination. And while we're on the subject of compasses, it's important to note that the north pole of a magnet is attracted to the south pole of the second magnet. But the north pole of the compass needle points to the north with that 11-degree declination. So the compass north pole points at the Earth's south magnetic pole. And as with electricity, like poles repel, as do like charges. Let's see. There are a lot of fascinating interactions between electricity and magnetism, and we'll get to those in the next few sections. All right, this is section 8.2. It's called Interactions Between Electricity and Magnetism. And we're gonna read over these summarizations here. And the first one is electric charges produce electric fields in the space around them. That's one. Number two is an electric field, regardless of its origin, causes a force on any charged particle placed in it. So that's electricity. Number 3, magnets produce magnetic fields in the space around them. A magnetic field, regardless of its origin, causes forces on the poles of any magnet placed in it. And that leads us to the observation 1 in your book on page 296, is a moving electric charge produces a magnetic field in the space around it. Therefore, an electric current produces a magnetic field around it. And once again, I'd like to urge you to look at figure 8.8. You see your electric current I is moving towards the right, and the circles go around the wire or whatever its a conduit is, and that represents the magnetic field. So a simple single charge particle creates a magnetic field only when it's moving. So only when it's moving. The magnetic field is produced in the shape of circles around the path of the charge. And this is illustrated quite well, once again, in that figure 8.8b. So please take some time and take a look at that. Hi, everybody. We're continuing. This is section 8.2. And we just got through observation 1, which states that a moving electric charge produces a magnetic field in the space around it. An electric current produces magnetic fields around it. And so now we're going down to this section here, which tells us that most applications of this phenomenon use coils, which are long wires wrapped in the shape of a cylinder, often around an iron coil. A coil whose length is much greater than its diameter is called a solenoid. And we have these in our cars. If an iron rod is partially inserted into the solenoid with a hollow core, the rod will be pulled in when the current is switched on. So solenoids are used for doorbell chimes, opening valves to allow water to enter and leaving washing machines, withdrawing deadbolts in electric doors, and engaging starter motors on cars and trucks. Electromagnets are used to produce the strongest magnetic fields on Earth. 2 factors contribute to stronger fields: wrapping more coils, so more ends, N is the number of wraps, and using a larger electric current. So larger eyes, larger number of wraps produces a stronger magnetic field. The polarity of an electromagnet is reversed if the direction of the current is reversed. Now we come to observation 2. Observation 2 says a magnetic field exerts a force on a moving electric charge. Therefore, a magnetic field exerts a force on a current carrying wire. A curious characteristic of electromagnetic phenomena is that the effects are often perpendicular to the causes. So what do we have here? We have electric motors exploit this electromagnetic interaction. The simplest type of electromotor consists of a coil of wire mounted so that it can rotate in the magnetic field of a horseshoe-shaped magnet. A direct current flows through the coil. The magnetic field causes forces on the sides of the coil, and it rotates through the coil. Once the coil is completed half a rotation, a simple mechanism reverses the direction of the current. And what I would like you to do here, I usually bring a demo to class, but since we're not coming to class physically, I want to urge you to just check out online. I'm sure there's many YouTube videos that demonstrate a simple 2-brush electric motor. It's very, very interesting, and I think you guys would like it a whole lot. Now we are on observation 3. Observation 3 states, a moving magnet produces an electric field in the space around it. A coil of wire in motion relative to a magnet has a current induced in it. This is called electromagnetic induction. And as we can produce an electric motor with a charge and a magnet, we can also use work to produce an electric current. We can reverse this electric motor and produce what is called a generator. So we can make a generator by doing work with an electric coil and a magnet to produce electricity. And this is how wind turbines, for example, make electricity. Another application of this technology is called regenerative braking. Okay, and once again, to reiterate, the interactions between electricity and magnetism described in the previous section 8.2, along with other similar observations, suggest the following two general statements. We might call these the principles of electromagnetism. One, an electric current or changing electric field induces a magnetic field. Remember, around that electric current. We can call these eddy currents, if you will. And two, a changing magnetic field induces an electric field. All right. Now we are going to use an AC current to produce what's called a transformer. And we touched on this in a prior section. And so example A1 is a nice one to go through, and it states that a transformer is being designed to have a 600 volt output with a 120 volt input. If there are 800 turns of wire on the input coil, how many turns must there be on the output coil? So we know, if you recall, we did a problem like this, and we have voltage in, it's a simple ratio, over voltage out equals number of turns in over number of turns out. So we have 600 volts over 120 volts equal NO over voltage in. N in, which is 800 turns. And so our answer is going to be NO equals 4,000 turns. So what we do is we cross multiply and divide. We get a 600 volts times 800, number of turns, equals 120 volts times NO. And dividing both sides by 120 volts, this cancels with that. We get our number of turns out to be 4,000. And these principles are used in sound reproduction, in microphones, and in speakers. So how does that work? You have I urge you to look at page 305, where you have a very good, useful diagram here. You have a south and a north magnetic magnet, and you've got coils wrapped around it. And this is called a diaphragm right there. You speak into this microphone, which moves the diaphragm, the air molecules, back and forth, causing the coil right here to move back and forth, producing a voltage or inducing a current. And so this is a, if you will, a blueprint of what you say, a blueprint of your speech pattern. This comes out to a speaker, and you can see this on page 306, which moves a cone, does the exact same opposite. The coil makes a cone move, and it produces vibrations in your paper cone, and this is how your speakers are produced. speakers and microphones. Very simple, but very sophisticated at the same time. Now we're going to talk about digital sound. Okay, so in your book, a process known as analog to digital conversion, the sound wave to be recorded is measured and stored as numbers. For CDs, the actual voltage of the AC signal from a microphone is measured 44,100 times per second. And this is recorded, the voltage. So what you have here is you have, instead of being a continuous wave, you get little spikes measured at this rate, 44,100 times per second, which your ear cannot really discern. So a lot of audiophiles prefer the analog sound, but the human ear cannot hear this type of frequency. So even though the sound is chopped up, it occurs so many times per second and so quickly that we cannot really discern this. And our digital music production systems are really good. Section 8.5 is on electromagnetic waves. All right, eyes, radios, television, radar, X-ray machines, microwave ovens, heat lamps, canning lamps, they all use electromagnetic waves. The electromagnetic wave involves both electricity and magnetism. It's a transverse wave consisting of a combination of oscillating electric and magnetic fields. They do not, from our little chapter on waves, which recall that some of them required a medium through which to propagate. Electromagnetic waves do not require a medium through which to propagate. They can propagate through a vacuum. And they all do that at the speed of light. In fact, all electromagnetic waves, in a scientific sense, are considered light, even though only a small bandwidth of them are within our visible spectrum. But they all propagate at c, the speed of light, which is 3 times 10 to the 8th meters per second. Your book gives you a different value, 299,792,458 meters per second. We can go ahead and use this value. That's fine for us. Okay, so let's look at example 8.2. 8.2 says, an FM radio station broadcasts an E&M wave with frequency of 100 megahertz. That's going to be 100 times 10 to the 6 hertz. What is the wavelength of the wave? Now, if you recall our wave equation, V equals F lambda. In this case, V is C. So C equals the frequency, 100 times 10 to the 6 hertz times lambda. So lambda is going to be simply 3 meters, because this is 10 to the 8, 3 meters. So we've used our wave equation and the fact that these electromagnetic waves all propagate at the speed of light, c, 3 times 10 to the 8 meters per second. And we like to lump these electromagnetic, we like to separate them into the bandwidths. So from the lowest frequency to the highest frequency. So this is lambda is very, very large, and F is very, very small. And right here, you're going to have lambda very, very small and F very, very large, right? Because they all have to travel at C. So if they all travel at C, when lambda is large, the frequency is small. When lambda is small, the frequency is large, if we hold C constant. So we start with down here, radio waves. And they're the lowest frequency. They're from less than 100 hertz to about 10 to the 9th hertz. They're used to produce radio sounds, low frequency radio sounds. Television, much communication is done with radio waves. This would be this frequency, radio waves, that bandwidth. Next, you're going to have microwaves. And microwaves are used in our microwave oven. That's because our microwave ovens work by exciting the water molecules in our food. You probably know by now that you cannot heat up dry bread or powder or anything like that. If you want to put something in the microwave oven to heat it up, it's got to have water in there. So it's the next band, and they're in the about 10 to the 9th to 10 to the 12th hertz. Our next bandwidth is going to be infrared, IR. Those are about 10 to the 12th to 10 to the 14th. These are heat radiation. We radiate, human beings radiate heat in this bandwidth. Okay, it's used in wireless remote controls for television, short distance wireless data transfer. This is what this bandwidth is used for. Our very small bandwidth is visible. So this is the bandwidth which human beings are capable of perceiving with our eyes. We can see visible light here. Finally, we've got ultraviolet, UV radiation. It's about 10 to the 14th to 10 to the 18th hertz. And right here, you've got just a small bit of 10 to the 14th in the visible range right here. It's the radiation emitted by very, very hot objects. For example, our sun. Let's see. Some substances undergo fluorescence when irradiated with UV. I think they do that with forensics to find blood in carpets and whatnot. Next, we have X-rays. They're 10 to the 16th to 10 to the 20 hertz. And we are all should be very familiar with this. They travel through most matter, but not bones. So that's why, or teeth, right? That's why we can use them in medical applications so nicely. And finally, we've got gamma rays. And they're 10 to the 20th to 10 to the 23rd. And these are emitted by nuclear reactions, right? Radioactive decay, nuclear fission, fusion, and so on and so forth. So this is our bandwidth, and it's a nice thing to become familiar with, all right? The various bandwidths of electromagnetic waves or light waves. Very nice thing. It's all in your book. It's covered quite intensely in your book. Section 8.6. Section 8.6. Section 8.6 covers black body radiation. So every object emits electromagnetic radiation because of the thermal motion of its atoms and molecules. We've already seen how this heat radiation is one method of transferring heat. Once again, human beings emit infrared radiation. Okay, so the power emitted by a black body radiator is equal to approximately equal to the temperature in kelvins to the 4th power. This is, you want to know the power of a black body radiator, it's the temperature in kelvins to the 4th power. On page 317, you have a picture of the radiation emitted by a black body radiator, and this is the intensity, and this is the wavelength. And as a black body radiator gets hotter and hotter, the wavelength at which it radiates gets smaller and smaller. So that would be a hotter object, and this would be a hotter object even yet. If you would like to know the wavelength at which an object radiates the most black body radiation, the formula is lambda max. So that would be this peak here, lambda max, is going to be equal to 0.0029 divided by the temperature in kelvins. So these two are very good equations to know and love. We'll be using them. Our final section is detection of warm objects. And it reads that most things on Earth have temperatures that cause them mainly to emit infrared light. Anything that can detect IR wavelength can use this fact to locate warmer than average objects, since they will emit more IR radiation. Rattlesnakes and certain other snakes use infrared radiation to hunt mice and other warm-blooded animals at night. These snakes have sensitive organs that detect the higher intensity infrared emitted by objects warmer than their surroundings. Infrared sensitive photographic film, video cameras, and other detection devices have many practical uses. For instance, IR photographs, called thermograms, can show where heat is escaping from a poorly insulated house and can detect ohmic heating caused by short circuit in an electrical substation. So that concludes chapter 8. A summary for chapter 8.